Let's get started with this shoot. It's all about lighting. So I'm going to share my screen. Oh, wait, share the screen. Okay. Okay, so let's see. What happens if we run the cheat code that I sent the link to in the Discord? We get a car, and it's looking a bit off. We see that it is textured because that's the top of the car is textured, but the rest of the car that should be yellowish is just white. So our goal for the first part of the shoot is to use the diffuse of the car, the diffuse coefficient to make it look like the orange color that it should be with shading. So let's try and do that. But first of all, let's do a brief recap of the system we have so far, because it can be a bit confusing. It's a bit complicated, but hopefully this simplifies it down a little bit. So at the very center of this graph, you have your scene node, and that's in the scene.cpp. In the scene.cpp, we also have stores one model which contains multiple meshes and materials. In the scene node, of course, you can translate it, rotate it, and scale it. Right now, we're focusing on if the model already does the normals for you, we can load a model in with normals and initialize the mesh template that it gives. Oh, actually, that's already done in the model load, and then we store it into the mesh vector of the model struct, and that's it actually. So it's the first part of the system. That's all we need to know to do the first part of the shoot. So how do we actually get back that reddish color or orangish color of the car? Well, we'll see that in the fragment shader, before we have a struct.material. So this is a way we can kind of group uniform variables together, and we create a struct out of it. And I'll show you how you can actually set variables inside structs later on. But the idea is we create an instance of the structs. So we call it umat, and then we can have umat.textFactor. And so this is how you can use the variables. This isn't much different from last week. The only difference is we have color instead of diffuse. So we're using color as a placeholder for in the case where there isn't a texture. Now I'm doing this because, I like this font. Oh, thanks. We're doing this because we actually want to use the diffuse for lighting, not as a placeholder for the color if there's no texture. Yeah, so that's why it's white, and the color by default is white. So let's actually color in the car by creating a vec3 for diffuse. Then we could do umat.diffuse times color. So that should give us the red color that we had in the previous shoot. The thing is, frag color is a vec4 and umat.diffuse is a vec3. So we can multiply the color's RGB value, umat diffuse, convert the whole thing to a vec4, and for alpha we could use color. Color's alpha. Okay, so that should do it for us, but you'll see that we need to do this a lot. We need to create a variable storing the location of the new diffuse color that we just created. Let's call it mat diffuse location. And then in the renders initializer, we need to set the mat diffuse location to be umat dot. So umat is the name of the instance of that material struct that we create in the shader, and umat dot diffuse. That's how we can grab the location of a variable inside a struct in the shader. Once we have that, we can set it within the draw function, which is a recursive function, and this gets called for each node in the scene tree. So in this case, we want to set a vec3 fv, the mat diffuse location with the mat materials diffuse. Okay. So let's see what happens if I run this now. Hopefully we get a colored car like from last week. So nothing's really changed if this works. Okay, yeah. Now you can tell that there is no shading on the car. So the goal of the first part of the shoot is to shade it in so that it looks a little bit more realistic. This shoot, we only focus on directional light. So that means every vertex, every fragment in your world receives the same angle of light, receives light at the same angle, no matter where that fragment is or that position in the world is. How do we do this? Well, let's go to the drawing board. So let's kind of come up with the diffuse equation. So given your object, which is represented by this line, and your object at a particular fragment that we're currently focused on, has a normal. And this normal is essentially a vector that is perpendicular to the surface of the object. So this is the normal. And we also have some sunlight coming in, trying to light up this normal, because this is directional light. It doesn't matter what fragment we're at, it's always the same direction, trying to get to that fragment. So this is the sunlight, right? So this is the sunlight vector. It's pointing from the source of light, which in this case is no real source, and to the fragment. But you'll see that we actually want the negative sunlight. So let me rub this out. Want the negative sunlight for the calculations that we're about to do. Okay, so the idea for diffuse light is if the angle between these vectors is large, say for example, the sunlight is perpendicular to the normal, then we don't want to light up this fragment at all. So you want some factor to be 0. What if the sunlight is directly the same direction or exactly the same as normal? Then we want to light up this fragment as much as possible. So we want the factor to be 1. And if you get this using the dot products between the sunlight and normal. So dot product between negative sunlight and the normal. So this is the factor that will go within the range. Actually, put this here. Within the range of 0 to 1 in the case where the sunlight is not somewhere like here. So what happens in the case where the sunlight is here? Let's call this sunlight 2. So let's call this negative sunlight 2. Now, the dot product of negative sunlight 2 and the normal is actually less than 0 in this case. The idea with the factor is that we want to scale the color of this fragment by this factor so that if the sunlight isn't directly facing the fragment, then we want to have a low amount of light on it. So we want to make sure that this is close to 0, but not less than 0. So in this case, we actually want to take the max of the 0 and the dot. Now this is actually in the range between 0 and 1. Yes. So let me actually move this. So the diffuse equation is essentially equal to the sunlight's color. Let's call it sun dot color times the factor, which is in the range 0 to 1, times the materials, materials diffuse. Then we can use the diffuse just like we have before. We multiply that by the color of that we get from the texture. That's it. So let's try implement that within the fragment shader. So we need the sunlight direction and the sunlight color. So let's put all of that in some kind of struct called directional light. Vec3 of direction, and we also need a color. And just following the formula we just came up with is called, we have a vec3, which is diffuse, and that's going to be, we have to first create an instance of the directional light, and let's call it use sun. So we use sun's color times the materials color, so u mat.color, diffuse, times the factor. So that's the max of 0. It's actually also called cosine distance, because it's really just the cosine of the angle. That's what the dot product returns. I think, yes. So you have u sun's direction and normal. Do we have the normal yet? No, we actually had to calculate, pass in the normal from the vertex shader, so v normal here. We haven't done that yet. And then after we've calculated this diffuse, we just replace umat diffuse times colors RGB, the same we did before. And that's diffuse for you. That's all it is. Thing is, I have to pass in the normal. And the normal is located on position 3. It's just the way I've defined the, you'll see why if you take a look at the mesh.cpp. So it's vec3, it's an attribute, it's the normal. And we need to pass it to fragment shader. So here we could say v normal is equal to a normal. The thing is, the a normal is relative to the original position of your mesh. But what happens if you rotate your mesh? Then the normals should also change. Oh, what happened to location 1? That's a good question. Location 1 is for your color. A color. In the case, just in case we do have color, but we don't. Yeah. Because some of the objects we want to render with this shader could have color per vertex. It's kind of a rare case though, because otherwise you'll get like a rainbow kind of effect if you want different colors per vertex. Yeah, so what happens if you rotate your mesh? Then that means the normals should also change. It should also be rotated. That's why we need to multiply the attributes normals with the model matrix. And that's the model matrix. So here we've actually separated out the view, the MVP to just M and VP. So we could actually do this U model times the A normal, except the U model is a mat4 and A normal is a vec3. So we need to make this a vec4. And then because V normal is a vec3, we could say XYZ. Like this. This should work. All right, so we've passed the normal to the fragment shader. And in here, we could read it in vec3 V normal to be used here. Now let's make sure we've grabbed the location of direction and color in the renderer. So that means we could do glint. Let's call it sun direction location. And we also have glint sun color location. In the renderer's initializer, as always, I need to grab the locations of those, doing renderer.sun direction location is equal to chicken3421, get the uniform location of that from the given the program. The name of it, well, we actually haven't created an instance of this. Oh, we have directional usun. So it's a usun dot direction. Do the same for the sun's color location. Sun color. Okay, cool. Now that we have these two, we could set them in the shader to be some values. Now I've already defined the sun's direction here. So the sun's direction in this case is a vector in the same direction as some point at 50, 50. So 50 in the X, 50 in the Y, pointing down towards the origin. All right, so that's how you can calculate a vector from one point to another point. You get where you want to go minus where you came from. And then we normalize that so it has a length of 1. So that's the sunlight direction. And we also have sunlight color, which currently is set to yellow, but let's just make it white. And we'll get to the ambient later. So in the renderer, we grab the locations, but we also want to set these values when we render the scene. We don't want to do it in the draw function because the draw function is called for every object in the scene. We only need to do it once per render, per frame. So we can say we're setting a GL3FV because it's vec3. Then we do renderer dot the location of what we want to set. In this case, it's the sun's direction. How many we want to set, 1. Then convert the value to a float star by using glm value pointer. So the value you want to set is it's called sunlight direction. And we also want to set the color as well, so color location. So sunlight color. Nice. So we've set these values, that's all good. Let's go back to the fragment shader and see if we've missed anything. So we've got the direction, the color, we've set those. We've set all of these, and the diffuse is going to be working like normal. So let's give this a run and see if it works. That's usually how it goes. Oh, nice. We get a shaded car, and it looks way more realistic than before. Now that we set the position, the sun's color. No, sorry, we set the sun's position to be 50-50. So that means somewhere up there. So if we go like this, we see, oh yeah. Yeah, we could tell the sun is to the right of us because it's kind of lit up over there. But then, yeah, the sun doesn't really work well with this sphere map. Sphere box. I don't know what to call it. Anyways, if you look at the car from this side, the triangles that are facing opposite to where the sun's pointing are completely black. So how do we fix that? Or maybe it's what we want, but actually in real life, that's probably not what we want because light bounces off objects and everything kind of gets lit up. That's what ambience is, the ambient lighting is. So how do we do ambient lighting? Well, let's go back to the drawing board. It's pretty simple. Ambient lighting is equal to the sun's color, again, times some factor, some ambient factor. So we could say the sun's ambient. And this could just be a float. So the idea of ambient is you just provide some base, some base color to everything. This means, if you think about it, do you think we should multiply the diffuse with the ambient or add diffuse and ambient together? We're not trying to scale the diffuse with the ambient. We're just trying to have some baseline color, which means that the frag color is just going to be the ambient plus the diffuse times the color. And the color we get from the textures, or if there's no texture, that's the user-defined color. And that's it. That's ambience or ambient. I've been listening to a lot of ambience YouTube videos, so I keep saying ambience. Ambience, you just make it a float. That means, like always, we need to do some bookkeeping, keep track of the location of it. Sun ambient location, and set it within the shader. Sun ambient location to be equal to sun ambient. And here, well, in the renderer, we set the sunlight ambient to be 0.1. That's generally a reasonable value to set it to be. You were setting a single float. So we set dot sun ambient location to be renderers ambient, sunlight ambient. Okay, so we've set up the ambient. Now we can use it. How do we use it? Well, we just calculate ambient as a vec3. And it's going to be the sun's color times the sun's ambient. Some baseline color we can use here. We just add it to the diffuse, like ambient plus the diffuse. So let's run that. Okay, kind of looks the same so far, but if we go here, we see that it's no longer black. There is some baseline color to it because we're assuming that everything is lit up to some degree. Cool. That's the first part of the chute done. Now onto the second part of the chute, which is about how do you create normals. So right now, the normals are created by the people who made that car model. We created our own shapes within shapes.cpp. So we have a make sphere, make torus, make cube, make torus is new. But these return a mesh template that only fill up the positions and the text coordinates, as well as the indices. And that's about it. They don't calculate normals. So what I've done is in the main function, I've added some stubs called calc vertex normals. It takes in the mesh template that a make shape returns. And all it does is it modifies the template so that it adds normals. Then later on, we could initialize it and add it to a scene node. Now let's think about how we can calculate the vertex normals. So let's create a new drawing board. All right, so let's say we're given a mesh template, and then in the mesh template, we assume there are indices. Now the indices define triangles. Every triplet of contiguous of indices define a triangle. So if this is I, this is the index I, this is index I plus 1, this is index I plus 2. See that this defines a triangle in counterclockwise order so that we can actually see it from our perspective. Does anyone have any idea how we can actually calculate the normal to this triangle? So this is where the cross product comes in. So the cross product takes in two vectors, and from those two vectors, we can calculate a vector that's perpendicular to both of those two vectors. Given a triangle, we have 3 points. We can calculate two vectors from those 3 points, take the cross product between them to calculate normal, and that normal is perpendicular to the triangle. So that's the idea. So let's say we have a vector calculated from I to I plus 1. We'll call that A. We have a vector from I to I plus 2. Call it B. Now the cross product between A and B should give you a vector that's perpendicular to both, regardless of whether A and B are normalized or not. So, but after we get the perpendicular vector, we can normalize it using just the GLM normalize function, which converts it to a vector of length 1. Now this is the normal. So actually, let's move this. So this is the normal. That's basically it. That's how we calculate what we call the face normal. So that normal would be something like that. But the problem is we want the normals to be attached to vertices. Right now, there's only one here, but we have 3 vertices. So we could just assign this normal to be the normal of all 3 vertices. That's what we call face normals. But the problem is these vertices could be part of multiple triangles, like this. So this vertex here is part of 2 triangles, which could potentially have a different normal. So for this vertex here, should the normal at this vertex be the right normal or the left normal? And this depends whether we want to calculate face normals or vertex normals. So for vertex normals, we take the average of the 2 normals and use that as a normal to the vector. For face normals, we take both. So since we have one normal or one-to-one mapping between vertices from positions and normals, we actually need to duplicate the position of this vertex so that we can assign 2 normals to it. So right now, let's just focus on vertex normals. We just have one, we don't duplicate vertices, so that means we can only have one normal per vertex. So we have to average between the 2 normals. And that's basically it for how you can calculate vertex normals. So let's try give it a go and see. But before we do that, let's see what happens if I try and create a sphere without lighting, without normals. So let's create a scene node. And we want to create a sphere mesh template, which will be equal to shapes make sphere. Give it the radius of 1. Then we could push the initialized mesh to the model, to the model's meshes, by doing mesh initialize the sphere mesh template. You can add a texture as well. So model.materials.pushback. You have to make sure that the size of the meshes matches the size of the materials. So we could push back struct. So let's take a look at the material struct, see how it's defined. Maybe model material. So material just contains the texture, color, and diffuse right now. They all have default values. That's okay, but let's say we just want to set the texture. A neat way to set the texture is to do dot texture within the curly braces is equal to texture to the init, an earth texture. Right, and then we can position let's just position the car away. So we can do car dot translation to be equal to glm vec3 1. Let's do 310. Then we could push back the sphere. Okay. So currently this sphere doesn't have any normals. So all the normals would, I think, be initialized to 0, which would cause it to be black. Yeah. So right now the sphere is black. And I can also translate the sphere so that it's 0, 1, 0. It's not in the ground. Now let's try to make it not black by calculating normals for it. So given a mesh template, fill up the normals vector by modifying the argument. To do this, well, going back to the drawing board, these indices, we're not guaranteed this is equal to 0, right? We're given a bunch of indices that could be like, 50, 0, 1, 49, so on and so forth. But every triplet of indices would make a triangle like I plus 1, I plus 2. So if we're going through every triplet of indices, you probably need to initialize the mesh templates normals vector to be an empty array of 0 vec3s. So we can say mesh template dot normals is equal to a city vector of GLM vec3s of size. Okay, what would the size of the normals be? What other attribute? Well, actually, it's kind of obvious. So since we said that each vertex has a normal, then it should be the same size as a number of positions. And we'll initialize each of the normals to be GLM vec3, to be a 0 vector. So later on we could average over. We could just add normals to this position, to any position. Yeah. So let's go through all the indices. How many indices are there? Well, there's mesh template dot indices dot size, many of them, and we want to go through every triplet, so we have to add 3 at a time to the index. We have to grab the actual indices that we are dealing with, so we can say auto I1 is the first index is equal to mesh template indices at I. We have 3 of them, so I1, I2, I3. This will be I plus 1, and this will be I plus 2. Now to calculate the normal, we first have to calculate what the A and B vectors are. So just make it clearer again. This is the A vector, right, and this is the B vector. So we say auto A is equal to, right, to get a vector in that direction, we have to say positions at I plus 1 minus positions at I. Should be I1, I2. Yeah. Let's actually get the handle on the positions, so we don't have to type so much. Positions is a reference to the mesh template positions. Okay. And then the B vector would be I3 minus I1. Then the normal is the cross product, normalized cross product between them. Okay. We've calculated the normal, and we know that the normal at each of the corresponding to each of these indices should be affected by this normal. It's not, of course, it's not equal to this normal like entirely. So what we can do is we can say that at a particular normal, at normals I1, we could say that this is equal to, we say that it's plus equals to the normal, right? So because we actually don't know how many this vertex could be part of many triangles, right? We don't know how many. So what we do is we can just keep adding these normals that we calculate to this vertex. And at the end, do one final loop through the normals and just normalize everything using GLM normalize. So we do that for each of the affected indices. So we can go through each of the normals and mesh template normals and do normals equal to GLM normalize the normal. And that's it. That's how we calculate vertex normals. Let me know if you have any questions about this. It's a bit hard looking at the code to understand it. It's more easier just like understanding using the diagram. Let's see if it works. We can do shapes, calc, vertex normals, pass in the mesh that we want to create normals for. And run the code and see if we get some shadows, not shadows, but shading. Yeah, nice. So we get the earth and we see it's shaded. To get a better look at the shading, we can rotate it. Yeah, that's the earth. It's reading. Okay, and we see that the earth is quite smooth looking. But what happens if we calculate face normals instead? All right, so for face normals, we need to attach multiple normals to the same vertex. This means we need to duplicate that vertex so many times, the appropriate number of times, which means that we can't use indices. So whenever we pass a mesh template into calculate face normals, we assume, we can say, a nice way to do it is expect that the mesh templates indices is empty. And say shapes, calc, face normals, expects the mesh template to have no indices. Something like that. Anyways, I provided a helper function called expand indices that takes in a mesh template and returns a new mesh template with no indices. And what it does is basically duplicates all the positions, text coordinates, if they are there, based on the indices. So to calculate face normals, it's really the same idea. It's just that every triplet, every contiguous triplet of positions makes up a triangle. This time, instead of the indices doing that. So we can just do it auto I is equal to 0, go through every triplet of, so we're going through the mesh templates positions or size. I plus equals to 3. And the calculation is exactly the same. So we could just say this, and paste that. The only thing is here I want I plus 1. Here it's I. Here it's I plus 2. You also need a handle to the position. Okay. And we want to push back to the mesh templates normals, the same normal 3 times. So basically the same normal for each of the vertices of that triangle. And that's how you calculate face normals. So let's see what happens if I use this instead of vertex normals. That means that I need to expand the indices first. So let me copy this to compare it. And make everything sphere add a 1 to everything. So I can tell them apart. Push back a sphere of 1, but this time I want to do calc face normals. And here I want to do shapes, expand indices. Okay, and also let's position it -3 in the X and spin it. Oh, okay. Well, it's hardly any difference so far because the tessellation is quite high. But this is the one that's supposedly using face normals. Let's make it a little bit more obvious by reducing the tessellation. So by default it's 64. What if I make it 16? Okay, so let's first look at the smooth one, the one using vertex normals. We see, even though the sides are jagged, when we look at it directly, we don't really see that it's jagged in the middle. But if we look at the one using face normals, we can actually see the edges of where the tessellation is happening. So essentially each face has a different shade to it, rather than a smooth contiguous change in the shading. Why did I say contiguous? I don't know. I've been saying that too much. Sometimes I don't even know what I'm saying. No. But that's pretty much it for the truth. The only thing is something cool I want to show is the Saru, so the monkey that everyone, there's kind of like the lighting hello world of graphics. It's called Saru, so I can load that in. Any questions, by the way, like or comments? So Saru's.model is equal to model. Wait, Saru.model is equal to model load texture, and that's Saru path. And let's give it a translation. Check 3 of -6, 1, 0. Then push it back to the children. Let's see, because last week we couldn't really see what this monkey looked like. It was just one gray blob, but now we should be able to see what it looks like. Yeah. That's the Saru model. And wait, I think it's a monkey called Suzanne. I don't know why it's called Saru in the, yeah. Anyways, we could tell it's using face normals because it's jagged. Like this sphere, not like this one. Yeah, that's nice. The car does look sick. Yeah, it's for sale. I would say around 2 mark coins, because that doesn't sound like a lot, but mark coins are worth a lot. Yeah, ton to mine. That's it. Wait, is there anything else we can do? Oh, the challenge exercise for the chute is basically, in the renderer, we have the sunlight's direction. Sunlight's direction, we can move around the world so that it changes. So your exercise is to be able to rotate the sunlight direction around so that to simulate night and day, and also change the color of the sun as it goes around as well when you press Q and E to change the sun direction, position, I guess. That's nothing we haven't seen before. So, I mean, in terms of theory. So yeah, have a go at that if you want. I mean, yeah. Oh, and I can also go through the rest of the diagram that I made. So this is just a summary of what of the system that we have so far, because it can get, I guess it can be a bit confusing. So you can make a mesh template which contains the positions and all the information that we need to send to the GPU. And then we pass it to calculate vertex normals to actually compute normals for it. We initialize the template to actually create a mesh, put it in a C node, and that's the other path. And a C node could be used as the root of a scene, which is then passed to the renderer with the renderer object that actually contains basically all the shader information to render it. Yeah, and that's it. Okay, let's call it a day. I'll stop sharing. All right. See you guys later. Thanks.